I see some chain rule for the cosine.
Absolutely. But this is just a function and this is just a function and you're adding them together. So you kind of look at it like it's like two separate problems. What's the derivative of E?
E.
Itself. Yep. Yeah, so the same thing, you're at it. And what's the derivative of cosine?
Negative sine.
Yep, negative sine x plus what's the derivative of cosine? You already told me it's negative sine x, but you keep the inside function. So we keep the e to the x, and then you multiply by the derivative of the inside function, which is e to the x. So I guess we don't need to clean up any of that. Anything there unclear?
Why did you put the negative sine x twice?
So this first one comes from the chain rule of that.
Oh, okay.
And then the second one is that's the derivative of that.
Okay, all right.
It's it's like joining two problems together there. So what's the next one here to look at?
Number 35.
Okay, so just in order there.
Yep.
All right. Okay, so 35. I saw one on a test recently like this with a student going to a review. There are two options here. Option number one is a quotient rule, which is a bad option here. Option number two is to use logarithmic differentiation first. The reason quotient rule is so bad is because in the numerator you have to do product rule again, and that's just horrible. So here, if you take the natural log of both sides, when you take the natural log of the left side, so imagine all that's in there, there's a bunch of things that simplify. So let me write it out and see if you are okay with this, or if you want me to do any explanation on this. So the net, when you expand the log of all of this mess, you get this on the right here. Is that would you like any review on that?
No, I get it. I understand.
You get it. Okay. So the reason this is so powerful is on the left, when you take a derivative, you get y prime over y. On the right, the derivatives of ln's are great. They're just 1 over x plus 1. Chain rule here is 1, so you don't even need to write that. Here it's 5 times 1 over 2 minus x. Derivative of 2 minus x is negative 1. 7 times 1 over x plus 3. So ln's are all just 1 overs. And maybe a small amount of cleanup here. It's 1 over 2 times x plus 1 minus 5 over 2 minus x minus 7 over x plus 3. Now, see how there's this y on the bottom? Talked about that a lot last night. The y ends up going over here because you multiply both sides by y, but y is that original thing that we did. So it ends up being, I'll just copy and paste here. It ends up being that original expression, and I'm gonna just snip it in because it's just a lot to write here. This is a good exam question because if you didn't practice this, you would potentially use quotient rule and really make a mess of it. But this is the best sort of way of writing the answer for this one. Like they want you to use logarithmic differentiation for this.
So how would you identify when to do log differentiation?
That's
just when it's easier.
Yeah, but how do you know it's easier until you've done a bunch of these? Like I'm on your side here, like saying it's hard to know. It's like you do enough problems, you eventually get it. So like 38. When you look at 38, what do you see? Let me snip it in here. Sorry, I guess that'll be better.
I see some quotient rule, but then you gotta do some product rule as well.
Yeah, so that's bad. That's where you would
Yeah.
hopefully say, let me do logarithmic differentiation on
Right.
this. So let's do this one together. On the left, it's natural log of y. You are taking the natural log of the right, and it becomes 4 natural log x squared plus 1. You bring that out in front, minus 3 natural log 2x plus 1, minus 5 natural log 3x minus 1. If you can do this step where you break apart the log, you're going to really make it even better. So do you feel comfortable trying to do the derivative step next?
Yep.
All right. So I'm going to write out the simplified form of this, or kind of the extra step here. So this becomes 6 over 2x plus 1. Maybe we'll just change that to 8x. Okay, so do you recall what to do from this point here to like get it done down to like y prime?
Yes, I do.
Okay. And then you always end up multiplying by y, which is the original, which is this all this stuff.
All righty.
Okay, so where do you want to go from here? So you asked me.
Let's go over to the second picture I sent.
Okay, so just to be clear, like the way you decide on logarithmic differentiation is you kind of are looking for ones that are hard to do product and chain rule kind of together. Okay, so these are a L'Hopital's rule. Which one do you want us to start with?
Let's do 66 through 69.
Okay. All right. Did you talk about indeterminate form in class today?
Oh no, we went over. Oh wait, I think it's the same thing. We went anti-derivatives.
Oh, really? So you're moving on. You're moving on past. Okay. So there's a couple of different types of indeterminate form. One of them is infinity over infinity, 0 over 0.
Oh, okay. Yeah, I remember those are.
Okay. So this is actually not in that form. So a lot of these L'Hopital's rule have a rewrite step to them. And again, if you don't know this, it's non-obvious. Sine x over e to the x. Well, actually, this one is not indeterminate form. So I take that back. This one you can rewrite, but you can also do it from the original. So do you know what sine x does when you what does sine x do forever? It oscillates, right? And it's bounded from like -1 to 1. Like it's either up here at 1 or it's down here at -1. Like forever. Do you see that?
Yeah.
Okay. E to the x, when you graph it, it goes like this. So it goes to infinity. So this is essentially asking you, and this is not quite right, but this is how you have to think about it. What is a number over infinity?
A number over infinity, it's 0.
Yes. So like this goes to 0. But this is not L'Hopital's rule. This is not an indeterminate form. So maybe 67 is. Nope, it's not. Is that the next one to do?
Yes.
Okay, like 69 is in indeterminate form, but I don't know if we get to it or not. So these
So
are
there's
just
no answer for that, or
no, the answer is 0. Sorry, the answer
okay.
here is 0. But there's like it's like these are all the things you have to think about to get that answer.
All right.
Okay. So in truth, like a lot of these have the answer of 0 or 1, or like if you have to guess on a test, like let 0 and 1 be kind of your guiding light on that.
Let me resend that picture so it's not blurry. I didn't realize the problems were blurry.
It's good enough for me if you're okay with that. All right, I'll download it here again and get that a couple of clicks here. All right, so let me go and get that. Refresh the page. All right, so let me grab 67 again here. All right. So limit as x goes to infinity, 1 plus 2 to the x, 1 minus 2 to the x. This is kind of infinity over infinity. And so what do I mean by that? What does 1 plus 2 to the x do, like the numerator, when x goes to infinity? Like, do you have a visual of what this graphically looks like?
Yep.
It goes like that. Like that's a growth function. Okay. The other one, 1 minus 2 to the x, this 1 doesn't contribute much. So this minus 2 to the x, it looks like that. It actually goes to minus infinity. But these, whether it's infinity over negative infinity, infinity over infinity, it's all the same.
Right.
Okay. So like before you knew, you did cover L'Hopital's rule, right? Like I'm not telling you something from, okay. When it's in indeterminate form, which we finally get one that's in indeterminate form, you take the derivative of the top and the derivative of the bottom. So like you look at just 1 plus 2x, the derivative of 1 is 0, 2 to the x is itself times the natural log of 2. The derivative of the bottom, derivative of 1 is 0. The negative comes along with it. Derivative of 2 to the x is 2 to the x times natural log of 2, but there's this negative out in front. Does this cancel? Does anything here cancel? Yes.
Yes.
Okay, and there's a 1 here, like sometimes we forget that, and there's a negative 1 there. So this equals -1, and that's your answer.
Okay.
So when it's in this indeterminate form, whenever you get one of these indeterminate forms, you have to take a derivative of the top and the bottom and the bottom.
Okay.
68.
Yep. I guess for me, it's just like
we do 69 first because it's more like the one we just did.
Yep. That's fine.
What were you going to say there? I'm sorry for interrupting.
I guess identifying if it's 0 over 0 or infinities.
Yeah. So the first step here is you try the limit value in the top and bottom. So that'll make a lot of sense here. Like, what is e to the 0? That's 0 minus 1 over tangent of 0. So e to the 0 is 1. 1 minus 1 is 1. I'm sorry, 1 minus 1 is 0. Tangent of 0 is 0. Right. This is 0 over 0. This is indeterminate form.
So what if it's infinity? What do you do?
Well, if it was like infinity over 0, we got a problem.
Or if the limit goes to infinity, I mean.
Well, we had that in the last problem, right? We had infinity over infinity. And that's L'Hopital's rule.
Yeah, like how do you identify if it's infinity over infinity?
Oh, you have to know the graphs. You have to know what happens at infinity.
Okay.
You have to know the graphs of all these.
All righty.
Which I know isn't a great answer because there's a lot of graphs, but that is truly what it is. Right. So when you get this indeterminate form, you have to take a derivative of the top and the bottom. It's not quotient rule. Never, never, never quotient rule, but it can maybe give that perception. So its limit as x goes to 0. Derivative of the x is e to the x. Minus 1 is 0, so you don't include that. Derivative of tangent is secant squared x. So then you try the limit again.
Uh-huh.
meaning you put that number in again. So it's e to the
Right.
0 over secant squared of 0. And like what you're hoping for is you're hoping like it gives you a nice value.
Right.
Okay. So e to the 0 is 1. Secant squared of 0 is 1. It's that, remember, secant is 1 over cosine squared. On the unit circle, cosine of 0 is 1. So it's 1 over 1 squared. It's 1. So that becomes the bottom. So this whole thing equals 1.
Okay.
Do you think you could replicate that on an exam?
Yeah, I'll practice it more, so I'll be able to do that.
Great. We are definitely gonna get to 68. I'm gonna do 71 next. Because there's sort of an order here to learning that if you don't do, you don't get. Like, you need to see a few more of these indeterminate forms.
Okay.
Okay. So first thing you do, you try the number. You try the number in there. Like, your instructor wants you to see e to the 0 minus 1 minus 0 over 0 squared. They want to see that you get 0 over 0 here. They have to see this.
Uh-huh.
You might even want to write, indeterminate form here. So now, like a good calculus student, you're like, all right, I got to take a derivative. Give me the derivative of the top, please.
That'd be e to the x
4x.
plus 4. Or e to the 4x. Yeah, okay.
All right, anything else?
Minus 4.
Very good. Okay. And then you try it again. And this is probably something you know in real life. You try something, it didn't work, or it worked, kind of worked, didn't, you don't really know. So you do something else and you try it again. Maybe if you worked on a car or something, you try something. So here, you can put 0 in again. So it's 4e to the 4 times 0 minus 4 over 2 times 0. And this again equals 0 over 0. Indeterminate form again.
Mm.
So guess what you do now? Take another derivative. Okay, so this becomes, the numerator becomes 16e to the 4x over 2. And you try 0 again. Put 0 in, so you get 16e to the 4 times 0 over 2. And you end up getting 8. So we applied L'Hopital's rule a couple of times here. Now, if you have a really certain type of instructor, they will give you problems. You have to do this like over and over and over again, but like a couple of times is what you might see on an exam. So we should do maybe one more of these 0 over 0 forms, and then move to like the infinities.
All right.
So I like 70 here. So you always try 0. And this is where you got to know your unit circle. Tangent of 0 over 0 plus sine 0. Does this equal 0 over 0? Like, is the tangent of 0, 0 and a sine 0, 0?
Yes.
Yes. You're over here on the unit circle. So now you got to take a derivative. So you got to know your derivative of tangent. Secant squared 4x times 4, chain rule, over derivative of x is 1 plus derivative of sine is cosine 2x times 2. So you take them independently. The top is independent from the bottom. Okay, so now you try 0 again. So secant squared 4 times 0 times 4 over 1 plus cosine 2 times 0 times 2. So secant squared of 0 is like cosine squared of 0, the reciprocal of it. Cosine of 0 is 1 because you're there on the unit circle on that nice point there on the edge. So it becomes 1 times 4 over 1 plus cosine of 0 is 1 times 2. So this becomes 4 over 3.
Okay.
Do you see the progression here? You try the number,
Yes, sir.
then you take derivative, try the number, and you do it until you that. So let's try 72 because it's an infinite limit.
Okay.
I promise we'll go back to 68 if you really want to do it. It's different than the others though.
Okay.
So this is now like, and this is what you're asking me, like, well, how do you know? And so let's look at the top and the bottom separately. So the bottom, do you agree that the bottom goes to infinity? Does x squared?
Yes.
And it's because you know that goes forever. The top though is composed of like 3 things. It's e to the 4x minus 1 minus 4x. And you have to know what grows faster. Does e to the 4x go to infinity faster than minus 4x goes to negative infinity? Like, do you have an idea of which one which is more significant? The e to the 4x or the minus 4x? Because like one wins out and there's a race. It's like
Probably e to the 4x.
yeah, this is your sports car and this is your Ford Focus. I drive a Ford Focus, so I'm making fun of myself in case you were wondering. It's not a sports car by any stretch. So this grows out. So like you basically ignore those and you say, well, what does that do? Well, it goes to infinity. But see how it's not as like direct as like putting the number in.
Right.
And that's where I think it's hard for students because you're kind of making an assessment and you're not used to doing that. You're just used to doing. You're weighing like, which is there. So it's in this indeterminate form. So you have to take the derivatives of the top and the bottom. So go ahead and take the derivative of the top, please.
It's 4e to the 4x minus 4
over 2x. So you actually get the same scenario here of infinity over infinity because 2x, like you look at the graph of 2x, it goes to infinity. And so does e to the 4x. That minus 4 doesn't matter because it's insignificant. It's like $1 billion minus 4 is still $1 billion.
Yeah.
All right, so now you got to take another derivative because it's the same indeterminate form.
Yeah.
So it's the limit as x goes to infinity. So what do you see here now? Like now you actually put infinity in and you get infinity over 2.
Yep.
So what does that become? Infinity. Because that's more significant than the 2. Now, could you have determined that from the beginning? Yes, but like that is kind of the right progression here to do it. Although from a grading standpoint, it's like, I don't know how you grade this unless your instructor makes it clear, like you got to show these at every step. Okay, where do you want to go from here?
Can we go back to 68?
Yes. Give me 30 seconds. I'll be right back.
All right.
All right, 68. So we have okay, so we have to the power of x. So do you recall from I'm going to rewrite this slightly. Limit as x goes to infinity, y equals limit of 1 plus 4 over x to the x. Do you recall like how to get a variable out of the exponent, like with the logarithmic differentiation? We end up taking the natural log of both sides. So this becomes x natural log of 1 plus 4 over x. I'm sorry, get that over here. Limit as x goes to infinity, 1 plus 4 over x, like this. Okay. So what how do we want to do this here? Do you see that this right here, the limit as x goes to infinity becomes 1 plus 4 over infinity in this part inside here? And 4 over infinity is 0, so it becomes this right here breaks down into the natural log of 1. What is the natural log of 1?
And then just 1?
It's 0.
Oh.
Okay, so then this is where I'm not sure how much of this is going to be clear. On the left side, it's the natural log of y. So 0 times anything is
0.
0. How do you undo ln? E. So e to the natural log of y equals e to the 0, y equals 1. And that's your answer.
All right.
Is any of that clear?
Yes.
Like, where should we go back? Okay. Sometimes I'm not sure. I
got some more problems.
Okay. Send them over, I guess. You new stuff to look at?
Yes. Yes.
Okay.
It's our chapter 4 stuff, some chapter 4 stuff.
Did you just enter the room again?
Do what?
I'm just trying to, I've got a new Zoom feature I'm trying to figure out. You didn't leave the room and come back in, did you? Okay. Although I did get a notification about the message. Maybe that was it. All right, there's that. Uploading that. All right, so
yeah,
I see that
in 1 through 3.
1 through 3 on the exercises.
No, the true false ones.
The true false ones.
Or wait. Just kidding. Yeah, the exercise is my fault.
Okay. All right, so it says to find the local and absolute values on the given interval. All right. So there's an approach here to doing this, like a recipe. The first thing is that you evaluate the endpoints.
This is just finding the maximum and the minimum, right?
Yeah, but we evaluate the endpoints, take a derivative, and then we evaluate the critical points. But you got to get these two numbers first.
All right.
And then like, because you're going to compare to those values at the end. Get my calculator opened up here. So x cubed minus 6x squared plus 9x plus 1. And then for 4, you get 5. So like right now, this is the min, this is the max, but that we don't know what happens in between those 2 points.
Right.
So the second thing you do is you take a derivative. So your f prime of x, just leave a little room here. Your f prime of x is 3x squared minus 12x plus 9. You set that equal to 0. And you solve for x. So here you can factor it's x squared minus 4x plus 3, and you get x minus 3, x minus 1 equals 0. Okay, now the two values are x equals 1 and x equals 3, but you have to check if they are in the window. So the window is from 2 to 4. So see how that's the only one that's okay?
Yep.
So you go back here and you find f of 3. So you put 3 in for x and you get 1. And then like what I like to do is try and make a little bit of a graph here, see what's going on. And you don't even have to be this, like you don't have to actually graph the points, but you can. I mean, you can if you want. Let me move these axes. Just redraw this. So let me try and show it to you 2 ways. So you can like actually say, okay, there's 2, 3, there's 4, 3, 1, and then 4, 5. Okay, so we don't know what the graph does, but maybe it does something like that. But this is the max. This is the min of that. So you figure out whatever number is the biggest is the max, whatever number is the smallest is the min. Okay, and those are the absolute extreme values. Okay, so but graphically though, we can see that that's the max, that's the min. This is also the local min because it's lower than the place below it. So I'm not sure how much of that you got into class, because there's some debate about like whether stuff is absolute or local min at the endpoints.
Right.
But you for sure can figure out which is the max, which is the min. And then the local min comes down to what the graph looks like. Like, is this point lower than the others? So I don't know, is that clear?
Yep.
Okay. What is the next? So 1 through 3. So obviously number 2. Great. So again, you follow the recipe here. You first start by evaluating the endpoints. So I'm going to snip that function in here, and you gotta figure out, okay, what is f of -1 and what is f of 1? Okay, f of -1 is negative square root of 2. F of 1 is 0. Then you got to take a derivative. What rule do you see kind of governing this right here?
Product rule.
Product rule. So it's x times 1 over 2 square root 1 minus x times -1 plus square root 1 minus x. And you set this equal to 0. This is where most students start to struggle, because they if your algebra is kind of good and then you get to a problem like this and you got to solve it, you got to very quickly know what to do. You actually want to move this term on the left over to the other side, because it's going to make it positive. So you're gonna have root 1 minus x equals x over 2 square root 1 minus x. And then you can cross multiply here. You can butterfly this right here. So it's 2 square root 1 minus x times square root 1 minus x equals 1 times x. The roots go away because they're both the same. So it's 2 times 1 minus x. equals x. So you have 2 minus 2x equals x. And then you add 2x over, so you get x equals 2/3 as your final answer.
Okay.
That's your critical point, though. That is not like the answer to this problem. So 2/3 is the critical point. Is it between -1 and 1? Yes. So we're happy. So now we got to go back and evaluate the original function at 2/3. So this is 2/3 times the square root of 1/3. You can see like this one's positive, this one's negative, this one's at 0. So this is your max. And I don't know what's happening. So if we made a quick sketch of this, at -1, it's negative square root of 2, so it's about there. At 1, it's 0, and it's up there. So it's almost like this point in the middle is nothing, because I don't know what it's doing in between here. But this is the min, and this is the max. Oh, I'm sorry. I didn't graph this right. I made that completely wrong. I'm sorry. Let's redo that. So at -1, it's negative square root of 2. At 1, it's 0. At 2/3, it's up here somewhere. So we actually do know it. Like it probably, that's your max, and that's your min.
Okay. All right. This is all fresh in my brain just because I did a quiz over all this stuff.
Okay.
Made 100 on that quiz, by the way.
Oh, really? Nice. Did you slam it on the teacher's desk when you put it up there and you said, I showed you?
I was actually like the second to last to finish, because
Okay.
when you had to find the increasing to decreasing values,
Mhm.
I messed up at first, and I'm like, this can't be right.
Yeah.
And so I did the rest because all the questions were related to each other.
Yeah, you don't get any points by being first.
Yeah. If I would have turned it in, then I would have gotten.
First and wrong is still wrong.
Yeah.
Doesn't matter here. So good. Yeah. Whatever you did, try to replicate that. In your studies, you'll find that you'll figure out the right ways to get this together.
Yeah.
Okay. So again, here you just evaluate the endpoints. So for some, it's easier than others. Like this one is a little more complicated to find the values, but you can certainly do it. So this ends up being -2, and then f of 2. I know you don't have a calculator, but I'm just shortening this up here. This becomes 2/5 for that. Then you got to take a derivative, which hopefully you see as quotient rule.
Yep.
So your derivative here is bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. Now you're setting this equal to 0. A rational function, when it's of this type, where it's p over q, this equals 0 only if p equals 0. Like that's so you don't need to like look at the bottom anymore. You're just like looking at the top.
Right.
So the top is 3x squared plus 3 when you distribute that in. 3x times 2x is 6x squared, so minus 6x squared, minus 8x plus 8x. So we end up getting minus 3x squared plus 8x plus 3 equals 0. As a reminder, you can actually like change the sign of all these to make it easier. You can also just factor it with a negative. My guess is you would probably make this positive. So 3x squared minus 8x minus 3 equals 0. They're not testing your algebra, so you don't have to do any sort of crazy thing here. But you got to be able to do some light factoring. So notice x equals -1/3, x equals 3. Are either of those in the window from -2 to 2? That one's.
No. Or yeah, the left one is, yeah.
Yeah, but that one isn't. So you gotta, like, even though it was nice, you gotta be like, oh, okay, yeah, that didn't work. So you gotta go back to your original and evaluate it at f of -1/3,
Yeah.
which I don't know if it's gonna be nice or not. It is. It ends up being -4.5 or 9/2. So this is the min, and this is the max. You just look at which is the biggest, which is the smallest.
All right. All those. I want to do number. Take all the pictures. All I want to do. All right, I'm gonna send you this one problem. This probably take the whole
Sure.
time, maybe. All right, there you go. It's the 9 through 14 one.
All right, let me get that.
Let's do number 9.
Okay. Okay, so there's a bunch of parts here. So we'll just do them one at a time here for this. So number 9, they give you this thing right here. And question part A is find the vertical and horizontal asymptotes, if any. This does not have any. This has none of each. So for vertical and horizontal, you're looking for like a rational function for that. Find the intervals of increase or decrease. So to do this, you need the derivative. Okay, so for this, you need f prime. So we got to first calculate f prime of x -2 minus 3x squared. And then you set this equal to 0 and you're looking for your critical points.
For the vertical and horizontal asymptotes, don't you need an equation above another equation?
Yeah, and that's what I meant by rationals. So it's like a p over q.
Okay. You get your vertical from the denominator.
Yes.
And the horizontal from the leading or whatever. Yeah. Got it.
Okay, so what you're going to find here is that this never equals 0. Like there is no solution to this. Like, okay, and you can check that later, but you'll see you take the square root of a negative. So that means you make your sign chart, but that you can just test any point that you want on there. So your sign chart here is like, looks like this. Like normally you put your critical points here, but there are none. So whenever you put a number here, this thing is always negative. And that means the original is always decreasing.
All right.
Does that make sense?
Yeah.
Okay. Ooh, this one's not real interesting. So because there's no critical points, there is no C, there is no, and I'm gonna snip this in, there's none here because there's no critical points. You know, local max and mins are like something like this, where you know there's one or something, but this one doesn't have any because it has no critical points.
Right.
So it's like this one's kind of silly. Okay, D, D, I think we can do. Find the intervals of concavity and inflection points. You got to find F double prime. So
Right.
F double prime equals, scroll back up here, I forgot it, minus 6x, minus 6x. And you set that equal to 0. And that equals 0 and x equals 0. So that's your possible inflection point. Okay. And we know for sure if it changes sign on the sign chart here. So you put your critical point there. And when you put in a negative number into minus 6x, it becomes positive. When you put in a positive number into minus 6x, it becomes negative. So yes, this is an inflection point. It's concave up from minus infinity to 0, where the plus is. It's concave down from 0 to infinity. So I think that takes care of D. E is to sketch a graph. We don't really have enough information to do this, but it's like it because it's going to look bad. We know it's decreasing everywhere, concave up. So it like you probably, it's concave up and then like that is what it looks like. But we need more information to be able to like do that, like intercepts and stuff. So
We're ready.
Okay, do you know what your exam covers on Friday? Have you looked at all the topics?
Yeah, basically everything that we've done. And then, or I can just tell you the whole list right now.
Well, my follow-up was going to be like, where do you stand on that? And if you haven't, like, that would be a good thing to do is look at each of those and be like, okay, I know it, I don't know it, somewhere in the middle, between now and then.
Tomorrow, we're going to be doing a lot of optimization problems.
Okay.
That's basically, it's like related rates.
Mhm.
So yeah, and I want a lot of practice on that.
All right. Well, if you need a lesson, I am available tomorrow. If not, good luck on your exam. And
All right.
thanks again for scheduling. I'll send you the notes out here shortly, next few
All right.
minutes.
Thank you.
Have a great night. Bye now.
You too.